presenter. Probably. I can always use my own otherwise. I don't know if it helps. It might.
So we now have Mirco Siercke who will speak about the preparation of ultra-cold polar molecule. Please.
Yeah, thanks. I'm kind of here from the experimental side of things, I suppose. I'm from Silke Osberghaus's group in the University of Hanover, and today I'm going to talk about how to make one of these long-range interaction systems. And in our case, it's ultra-cold polar molecules. We've already heard about Rydberg atoms and ions and those kinds of systems. In some sense, polar molecules are the most flexible because they have long lifetimes and you can kind of tune their interactions, but they're also the most, well, they're one of the trickier ones, I suppose, to generate. So I would first like to talk about why we try to do it anyways. Apart from the quantum many-body physics that we already heard about and that we will hear about a lot more, there's a couple of other reasons why you want to make ultra-cold molecules. One is they can help you find out about some fundamental constants. In this case, for example, the electron-electric dipole moment. And you might imagine, because a polar molecule is such a small thing with electrons in the middle, you might expect that there are huge electric fields inside of this molecule that will really polarize this electron if it has a dipole moment, and it will really cause an energy shift onto this system in case the electron is pointing one way or the other way. Another thing you can do with ultra-cold molecules, of course, is ultra-cold chemistry. That seems maybe a little bit boring because you're just going to look at two molecules colliding, but on a theory level, you could change the orientation of these molecules. You can put them in different eigenstates, and you can really kind of test the fundamental theories of scattering and of chemical reactions. But we're here for the quantum many-body physics. So let me see if I can show you how to make one of these systems. There's really two ways of making ultra-cold molecules. One is the straightforward way that everyone would say, why not just do that? Let's just take hot molecules and make them cold. It turns out that's a bit difficult. So people have started using somewhat an indirect approach, namely you take atoms, you cool them down to ultra-cold temperatures. That's something people have been doing for decades. And then you combine them into an ultra-cold molecule. We do both at Silke Osberghaus's group. I mostly work on this one, and I'll also present some data on the other one because this one actually works much better. This field here is still kind of in its infancy, and I would like to talk about our contribution to hopefully make this thing really take off. So first we're going to talk about directly cooling molecules. If you want to directly cool molecules, you have a problem immediately, and that's the molecules around us are rotating and they're vibrating. Rotational temperatures are generally about 4 Kelvin, 1 Kelvin or so. Vibration is a little bit more lenient, let's say. It's 10 to 100 Kelvin or so, but molecules around us are definitely rotating, and the energies of rotation are so large that if you want to do any laser cooling, you would need a plethora of lasers. Quite a lot. So what you first need to do is you need to somehow cool these rotations and vibrations. And the way people do that in real life is they just stick them into a box with cryogenic helium, which is 4 Kelvin. They ablate a target, which produces our molecules, and then these molecules start colliding with the helium, and we get 4 Kelvin hot molecules. And it stops the rotations and the vibrations. This becomes a problem, this helium, later, because when we now want to go beyond 4 Kelvin, we would need to avoid collisions with the 4 Kelvin hot helium. And so what we do is we open our box and we produce a molecular beam going out this way. The helium spreads much further than the more heavier molecules. And if we just wait a long time at the far end, which is at the door somewhere, we'll mostly get our target molecules, but they now have a velocity. But they're very cold. So kind of the field of ultra-cold molecules getting them directly is reduced to these three things, namely slow down these molecules, trap them, and then do evaporative cooling. So basically all these three things are what is done for atoms routinely. So the question is, why is that hard for molecules? The immediate answer comes about because as soon as you try to excite a molecule with a laser, there's no guarantee that it's going to fall back to its initial state. molecules can vibrate and they can rotate. Vibration doesn't have any sort of selection rule that saves you. Rotation has some, but in general, you're going to walk up a ladder here. And so in the end, what happens, because these rotational energies are so large and these vibrational ones are even larger, is you scatter one photon and you lose the molecule to the laser. In principle, for laser cooling of molecules, we want to scatter 10,000 photons, so we're kind of spot. How do you solve that problem? The vibrations are actually limiting these vibrations are actually done by choosing the right molecule. This is a picture, well, not a picture. This is kind of the electron configuration of calcium fluoride, which I call the rubidium of molecules. And the reason calcium fluoride is great is because calcium wants to get rid of, or it wants to share 2 of its electrons, but fluoride only wants to accept 1 of them. In room temperature, unsteady things, find calcium difluoride because of this, but with this laser ablation, we can actually generate calcium fluoride, and that means that this bond that's being formed is only being formed by 1 of the electrons. And that leaves this other electron completely free, so to speak, and if we excite electrically with a laser this electron, we should not change this bond in any way. So classically speaking, we should change the spring constant of this harmonic oscillator, and therefore we shouldn't start vibrating this particular object, so to speak. A bit more theoretically found sound is if you look at the vibrational wave function overlap, you'll find that it's very large from the electronic ground state to the electronic excited state. You'll see that if you start with no vibration at 606 nanometers, you excite it, you will most of the time fall back down into V is equal to 0. I don't know if you can see that, but it's a 97% probability that that's going to happen. Now that's already great, but I told you you'd need to scatter tens of thousands of photons in order to laser cool these molecules. It's actually not good enough. Fortunately, the decay into V is equal to 1 is 3%, and the decay into V is equal to 2 is already 10 to the minus 3%. So if we just include 2 more lasers, 1 for V is equal to 1, 1 for V is equal to 2, we can repump everything into the initial state, and now we can scatter 10,000 photons. So that's the vibrations out of the way. The rotations are, in some sense, easier to get rid of because it's not so restrictive on the molecule, and you use, in this case, selection rules. The rotation levels of the ground state or of any molecule, so to speak, are basically just spherical harmonics. So they have a parity change whenever you go add 1 quantum to this, just like an s orbital, a p orbital, a d orbital will have a parity change. And so a photon will need to make a parity change in order to be absorbed, and it can only change the angular momentum quantum number by plus minus 1 or 0. And so if you were to put yourself in n is equal to 0, you would see that you would excite to the minus state here, and you could fall back down to n is equal to 0 or n is equal to 2, in fact, the J3 half state. So that's bad. That's what I mean by you'll walk up a ladder, because this n is equal to 2, you could add another laser, but it'll fall down to n is equal to 4. So instead, people realized, wait, we don't start in n is equal to 0, we just start in n is equal to 1. And as soon as we start in n is equal to 1, we'll see if we stay here and we excite it to the positive here, we can only fall back down into this state. There is, for the keen of you, of course, the n is equal to 3 state here, which has a negative parity, but it starts at j is equal to 5 halves, and that's forbidden because of the selection rule of j is equal to plus or minus 1. Okay, so that's rotations out of the way. So in principle, everything is perfect now. Except this rotational little trick that we pulled was a little bit prohibitive, and this is kind of the big thing that people in molecular physics are fighting with right now, at least when you try to make them directly, and that's that we're now working on a type 2 transition. And a type 2 transition, a type is not usually, this lingo isn't usually well known unless you're a molecular physicist. Type 1 transitions are transitions that atomic physicists use. They go from j to j plus 1, and what you'll find is if you start yourself in any sort of ground state, and you, for example, excite with sigma plus, you will start running up this ladder, and you will end up in this case, plus 1 state. 2, and it will fall back down to plus 1, and you'll just keep doing it and doing it and doing it, and you'll scatter an infinite amount of photons if you really want to. A type 2 transition is what molecules have, which is from j to j or from j to j minus 1. And you'll immediately see that if I walk up this ladder, I'll end up in this state here or in these 2 states here, and there's really nothing for a sigma plus photon to do at this point. Right, so after 3 absorptions, we completely turn off our laser or our molecule to the laser, and we haven't really done any laser cooling yet with 3 photons. If you are keen with laser physics, you'll of course tell me, well, then you just shine in another laser and everything is perfect, and that is very true, very smart. what you end up with then is a lambda system where you have two ground states coupling to the same excited state, and you will get electromagnetically induced transparency, or in general, any sort of coherent dark states are going to happen here. Right? So direct laser cooling kind of is fighting with these dark states at this point. These coherent dark states you can kind of get rid of by detuning one of these lasers and with respect to the other one to destabilize them, or by applying a magnetic field to change the energy structure here. But this is kind of the big problem of directly cooling molecules. That doesn't mean it hasn't been done. This, for example, is a mod by Mike Tarbot's group in Imperial College. It is about 20,000 calcium fluoride molecules. Beautiful, but if you know anything about atomic mods, 20,000 is orders of magnitude away from where you want to be. You really want to be at 1 billion. And this is kind of the state of the art currently. Which is not to say that Mike Tarbot is an amazing experimental physicist. It just means that it's really hard to do these experiments. So what's kind of limited then if I just told you that everything is perfectly fine, that we can deal with everything? And the big problem is actually in this step right here. It's in slowing down the molecules. So trapping the molecules has been done. Evaporative cooling has in principle also been shown. These have all been shown to be fairly efficient, if you believe this one. But slowing down molecules is something that's very hard to do. In fact, there's about, I would say, 10 different techniques that have been devised, and none of them are particularly great. But they're the best that we had until now. So why is atomic slowing so easy and molecular slowing so hard? For that, I would like to first explain to you how a Zeeman slower normally works, which is how atoms are normally slowed, in case you didn't know. And a Zeeman slower basically is the following. You just have a source. In our case, it's this cryogenic buffer gas cell that I was talking about. For atoms, it would be an atomic oven. There's a beam coming out of it, and you shine a laser beam from this side onto the atoms or molecules in order to get radiation pressure and slow down the particles. Of course, you need to detune your laser because it sees the molecules are seeing this laser Doppler shifted, so you detune by the Doppler shift. And as soon as you slow down the molecule, you see that this Doppler shift changed, so you now need to change the laser. And currently, molecular, well, there's three solutions to this in principle. Either you change the laser in time, so you need to know when your molecule is coming, or you just shine in every single laser frequency that you have, which would be called white light slowing. Both of these methods are not very efficient. We can talk about that later, I suppose. But chirped light, which is where you change the timing of the detuning, only slows a small part of the molecular pulse. And white light slowing kind of just pushes everything to 0 and beyond, so you never actually get a lot of molecules in the trapping region. Instead, atomic physicists use a Zeeman slower, and there you don't need to change anything about your laser. Instead, when the Doppler shift changes, you change the atomic levels. So you introduce a Zeeman shift, and the Zeeman shift compensates for this Doppler shift, this change in Doppler shift. And you don't have to do it in time, because you know the acceleration of these molecules, and if they have gone here, you know the velocity change they've had, so you can just taper your field in order for them to constantly be on resonance. And the advantage of the Zeeman slower is that if I have a molecule, let's say at 300 meters per second, it's going to get slowed down to 0 here. If I have one at 30 meters per second, it doesn't see the laser until all the molecules are reaching 30 meters per second. That's kind of the big advantage of the Zeeman slower. And I'd like to just show that here. This is an initial distribution of molecules, for example, out of a buffer gas cell, would be 150 meters per second or so. And if we now apply a magnetic field and shine a laser onto the thing, you'll find that all the molecules are pushed down onto this narrow region here. And if we now start increasing the field in space to maybe get to lower velocities, you will see that we are going to go lower and lower and lower. This, of course, is a simulation, and it's a 1D simulation, so this won't look the same. It'll look similar in experiments, but this is a bit of an optimistic result. The important gray bar here is the part where you can start using these magneto-optical traps to trap your molecules. So this is kind of the region that we want to get to. Okay, unfortunately, the Zeeman slowing does not work for molecules, at least in this current form, and the reason is that we are on this stupid type 2 transition. The type 2 transition means that whenever we excite the 4 states down up here, we are going to fall into the 12 states that are down here. And in principle, all 4 are connected to all 12. And so we need to populate, we're going to populate all of these ground state levels. And we can, of course, shine in lasers to pump them back up and have slowing again. But we now don't have this knob of perfect field control because this state here has a different the tuning changed with field than this state here. So we can compensate for the Doppler shift of one of these states, but not of all 12 of these. And that's kind of why molecules until now are not directly cooled more than 20,000 nmol. And we thought, can we do something about that? And thought for a year and said no, and then we thought for another half a year or so, and then we said yes. The thing to do is to go to a very high magnetic field. A very high magnetic field down here actually simplifies quite greatly. It's the Fischbach regime. Basically, the rotation and the spin, they no longer really do anything, and it's only the spin components that do the spin that does something anymore. And if you squint your eyes, or if you have bad eyesight like me, this might look to you like a 3-level system. And this 3-level system is now pretty close to the 2-level system that the Seemannsloher was supposed to be. And so what we do is we shine in our slowing laser, and now we have the only problem of this 3rd level, which we solve by doing white light slowing on the slowing lever. So we have a very strong laser that pumps everything on the level 2 back up into level 3, and this here is a velocity selective, so to speak, a narrow laser that's now going to bunch everything up. Right? So that was our take on how to slow down molecules and make it efficient and hopefully get orders of magnitude in the mod. The problem at the time was that we didn't have any molecules and we didn't have any cryostat either for the molecules. So can we kind of show this effect in something similar to molecules? And the answer is yes, with atoms. Now, I said atoms are easy to cool anyway, so that's kind of cheating in your eyes maybe. But atoms have what's called the D1 line. All the cooling is done on the D2 line, and the D1 line is exactly a type 2 transition. It goes from 1/2 to 1/2. And so we can implement the system exactly. We have 4 lasers here that couple to this state, and we have a broad repurpose that couples to this state. This is more of a 4-level system than the 3-level system I described earlier, but it's actually pretty identical. And so let's see if this works. This is our initial distribution of potassium. Potassium is a lot lighter and it's a lot faster coming out of the oven because it's a lot hotter. At 400 meters per second, when we have the field on and we switch on our laser beam, we'll see that the atoms are being pushed up to 350 meters per second roughly. And if we then increase the taper on our field, we see that the atoms get more and more pushed towards 0 velocity, right? And this, we've compared this to a type 1, a normal Seemannsloher, and this is actually about 60% as efficient. So it's pretty to maximum efficiency that you could get. Just for comparison's sake, because I figure of merit, this is white light slowing, which is one of the techniques that molecule guys use currently, and gray bar that it doesn't really do as good of a job as Seemannsloher could. So we're expecting orders of magnitude improvement from this. We just now are setting up for actual molecules because nobody really cares about a Seemannsloher for atoms, I suppose, the type 2. Okay, so that's the way that we are planning on doing directly cooling of molecules, but of course this is still far in the future, so to speak, and you'd want to have a system now. And to have a system now, you'd need to do the second approach, which is to indirectly cool molecules. So what you do instead of cooling the molecules is you cool the atoms. In our case, it's sodium and potassium. The sodium is being slowed in a Seemannsloher, a regular Seemannsloher, not a fancy one. The potassium is coming from a 2D mod, and in the center here they meet, and this is where all the science happens. It's not too important, but this chamber is fairly flat and has electrodes on it, so you can create large electric fields once you have the molecules. That's kind of the experiment. This is actually the experiment that's being done in the room next to my experiment, but I hope I can answer all your questions if you have any. Okay, so the first thing to do is, well, how do we get from atoms to molecules in this case? Well, you'd first want to cool both species to BEC or close to BEC. Then you'd want to use a Fischbach resonance to create weakly bound molecules, and I'll explain that in a second what a Fischbach resonance is in case somebody doesn't know. Then you'd need to find an excited state with good coupling between this Fischbach state and the ground state. And then you need to perform a stir-up, which gets you to the ground state. Okay, this is kind of the data. It's just a quick, because I don't think I have too much time. This is our Bose-Einstein condensate of sodium, and this is our Bose-Einstein condensate of potassium. You can kind of see the bimodal distributions for the potassium. The sodium is already pretty pure, so you'd have to believe me that the tail here is not Gaussian. And we get about 20,000 sodium and 40,000 potassium, but this is subject to change in case we want to change the evaporation or the temperature. Then the next thing that we have to do is we have to go to Fishbach Resonance. And why do we have to do that? If you just want to combine two atoms that are anywhere in your trap into a molecule that is very tightly bound, this would be the place where a molecule would sit, for example, in the molecular potential. It's basically not impossible, but very hard. And the reason is that photons, which you're going to use to associate these things, they cannot change the position of the nuclei. So you're basically relying on luck that the atoms happen to be as close as this at the time that you're doing your experiment, and that luck is very unlikely to happen. So what you do instead is you first prepare a molecule that's very loosely bound, but much closer together than any sort of two completely free atoms would be. And you do that with a Fishbach resonance. And a Fishbach resonance is pretty simple to explain. If your atoms are coming in on this energy here, which is on the entrance channel, they will, of course, bounce on this potential and leave again, because that's the energy they have. But this is just one of the hyperfine levels of the molecule or of the two atoms, and the two atoms could be in a different hyperfine level. Right? You could excite one of these atoms to a higher energy hyperfine level, and that would, for example, then be on this molecular potential. And this molecular potential does not have enough energy to release the atoms again, if they get in there. Right? So if you could somehow get the atoms from this hyperfine configuration to this one, you could possibly trap them. Or you could form a molecule with them, right? And so a Fishbach resonance does just that. By tuning this magnetic field, or a magnetic field, you can kind of shift this red curve up and down as you want. And at some point, you're going to hit a resonance, where a bound state in this red potential is exactly, that has exactly the same energy as atoms. And as soon as that happens, you will see that in principle, the atoms can come in, they can form this molecule temporarily or for a very long time, and because they can just stick around for such a long time, you'll see that the scattering rate or the scattering length goes to infinity. It doesn't actually go to infinity, this is a two-body calculation, but you'll start seeing three-body losses before that happens. Right? So you have a lot of losses. The other thing that you will see is that this red state goes below the dissociation. You'll start to see a molecule with a binding energy in principle. Okay, so the first thing we need to do is we need to find a suitable Fishbach resonance, and fortunately for us, it's at around 200 Gauss, and this is a plot of the remaining number of potassium atoms and sodium atoms if we sweep our magnetic field. We just turned it on very fast, in fact, not sweeping. We hold it there for 40 milliseconds, and then we turn it back down, and we measure how many atoms are left. And if you remember, the scattering rate on a Fishbach resonance basically goes to infinity. So you have a lot of three-body losses. That's what you expect on a Fishbach resonance. And that's what we're seeing here. If we hold our field at around 196 Gauss, we start seeing a lot of losses, and next to that, we don't. Right? So we can infer from that, okay, here there must be a bound state getting close to our atomic threshold. Losses are, of course, not what we want. We want molecules. And to get molecules, you need to be slightly detuned from the Fishbach resonance. Now that you know where it is, you kind of change your magnetic field slightly higher in this case, and you get this binding energy that you would normally have. And to now associate molecules into this thing, you would just start your atoms in a different hyperfine state, and then with an RF pulse, you would then bring them down into the molecular state. That's what this graph here is. This is the molecular state, and this is the atomic state. So you, of course, have another state up here that's just the free atoms. And from this, you can get the binding energy. And once you have the binding energy, you kind of know everything about the Fishbach molecule that you've created. Okay, the lifetime of these Fishbach molecules is not very long. It's only 300 microseconds. So you need to be fairly fast in order to make these into ground state molecules. And that's just because they're so floppy, they're so large. So how do you then go from a Fischbach molecule, this is the wave function of the Fischbach molecules we create on this red potential, how do you go from that to the ground state potential? I said earlier that if you try to associate from here to there, photons cannot change the position of the nucleus. In fact, you can't directly go from here to here. Photons will only take you vertical. And so what you have to do is you have to kind of find a helper state for that. And the helper state that we have here is the C sigma and the B pi, in fact. Why is it two states? If you look here, this is a triplet state that the Fischbach molecules are in, but the ground state is a singlet state. And that's means we have to somehow flip the spin of one electron without flipping the spin of another electron, and that's not very likely. People thought for a long time that helium has there are two different heliums. And so in order to do that, in order to flip the spin, we need a state up here that's not singlet or triplet. Spin. And in order to do that, we find levels that are very close in energy, and as soon as they're close in energy, they should in principle couple together. And that's exactly what these do. And then if we can excite to this state, you can kind of see the green wave function here. This wave function has an overlap with our Fischbach wave function and an overlap with our ground state wave function. Right? So with this helper state, we can get from a Fischbach molecule to a ground state molecule if we're smart about it. And smart in this case means steer up. I probably don't have enough time to go into. How much time do I have? Oh, you're not watching. Then I have lots of time. 15 minutes. Oh, with questions. Okay. Okay, so a steer up, I'll get to it later, I suppose. But let's just naively say we could excite this state and then de-excite down into the ground state, and everything would be fancy and perfect. In order to do that, of course, we first need to figure out where this excited state is. So we need to know two things. We need to know what this pump frequency needs to be, and we need to know what this Stokes line needs to be. And in order to do that, we need to perform some kind of spectroscopy. The easiest spectroscopy that you can do is again just loss spectroscopy. So we just shine a laser on and see what happens to the atoms when they disappear. That's what this is. And you can see for the triplet sigma and the singlet pi state, this is the resonances that we got at 150 Gauss. You can fit a model to that with the transition energies and G factors and everything, and it fits pretty well. These blue curves, I have sigma plus, sigma minus, and the gray is pi light. The interesting thing is that the G factors that you get out of these calculations are neither the G factors for the triplet sigma nor the singlet pi, and that's exactly because these two states are mixed together. Right? So they're somewhere in between. And so from this measurement, from these G factors that we can extract, we can get the mixing ratio between the triplet and the singlet state. And it's about 25% triplet and 75% singlet here, and the other way around on this line. Right? So both of these in principle could be used for coupling to our ground state. We use the one that's mostly triplet behavior because the triplet is actually the one that has the Fischbach molecule in it, and if you remember, the Fischbach molecules are extremely spread out, so in fact this laser needs a lot more power than the other laser. Okay, the down leg, so we now know one of the frequencies that we have. How do we figure out what the other frequency is? The other frequency we figure out by basically just turning this laser on. So if I go back, we just turn this laser on to where we think the frequency is, and we see, does it change anything, right? This laser should in principle affect the level that it's coupling to. If it's very strong, it should introduce an outer-town splitting. If it's very weak, and we have coherence between these things, then we should see magnetically. And that is exactly what we see here. So this is a scan of the up leg of the pump laser that was called earlier. And this laser is basically held constant, and we see right here, there's the transition. So from that, we now know what the frequencies are for both of the lasers that we need. And now we can perform our steer-up. And this is our result, so to speak. But steer-up is a bit of a counterintuitive thing. It basically is the same as EIT, so to speak, but it's an EIT that's traveling. First, you start with your Stokes laser. That's the one that actually connects the ground state to the excited state. So your dark state, your EIT dark state, would just be the Fischbach molecules, which we start with anyways. And then you slowly change the intensities of these lasers to adiabatically change the dark state that you have into the one that's the ground state molecules. And you might be asking, why don't you just do a pi pulse? The good thing about steer-up is it doesn't rely on the pi pulse frequency. So if you have any sort of inhomogeneities in your system, steer-up doesn't care. This is an adiabatic process, and it's going to get you from Fischbach to ground state. That being said, not everything is perfect, and currently, the good thing, of course, is if you then reverse the steer-up, you'll once again see your Fischbach molecules. Right? So that's our detection. We first see our molecules, we see them all disappear, and then we see them come back. And from this 20% or 25%, we can get a steer-up efficiency of roughly 50%. This is very new data. This hasn't been optimized yet, so 50% is actually not great for steer-up. People have seen 90%. We're getting there. Well, I'm not, because I'm not on the experiment, but they'll be getting there. They're smart. Okay, so in conclusion, I've shown you two ways of producing molecules. One was the direct approach, where we've shown that Zeeman slowing might actually be possible for molecules. which could get us into the quantum degenerate regime, hopefully. And the indirect approach, which is maybe more interesting for you for now, because it actually produces dipole-dipole interactions and molecules and stuff. Currently, we have about, well, a lower estimate of 1,000 ground state molecules. If you ask the optimistic guy in the lab, he'll say it's 10,000, but he's optimistic. And this is the group. Maurice Petzold has just graduated. He's the guy on the direct slowing. He kind of did all of it, well, most of it, with me together. And Paul was a master's student during that time. Is now working on getting the molecules ready. The indirect side has Philip, who's new. These three guys, Torben, Kai, and Thorsten, are kind of the main guys. And Alessandro is the postdoc in that group. So he's kind of the glue that keeps everything together. And of course, this shining star in the center, Siercke. So thank you.
So just to understand the differences between the two methods. So for the first method, you can reach which number of molecules?
Currently about tens of thousands, let's say. But that's in a mod. So mods are still 100 microkelvin cold. You need to get 2 orders of magnitude more temperature. In fact, you